Hi, welcome to the EEVblog clean room, or not so clean room. Why am I wearing a clean room bunny suit, you might ask? Good question. Well, we've got the ever popular mailbag segment, very special one today. Inside this box is a whole bunch of semiconductor fab paraphernalia, courtesy of Vincent Himpe. He's called Free Electron on the EEVblog forum, and he's very kindly sent in a whole bunch of stuff. So it's very apt that I'm wearing a bunny suit. Let's check it out. And here is the complete clean room bunny suit. This is a three-part one. It's got a hood on, which goes on first, and then it's got the overalls, which go, the hood is tucked inside the overalls like this, and then it comes with knee-high boots like this, which then go over. This is way too big for me. This is like extra large, and I'm only 5'9" in the old money, slim build. So yeah, not exactly so parachute, do it, MC Hammer. You know, no, sorry, I can't do it. But yeah, these are anti-static, of course, with conductive fibers in them, and this is a typical bunny suit in any sort of clean room. Usually they'll have like a mask for the really serious clean rooms, and gloves as well, designed to stop any fibers contaminating the air. Basically, skin cells, a lot of dead skin cells just come off your body, clothing fiber, hair, things like that, designed to stop all that. And this is an old one. It has been washed many times. It's actually worn out. The conductive threading there doesn't pass the limit anymore, hence they expire them after a certain date. And that's why I've got this one here. And yes, you can wear your shoes inside. The boots are really big, and you can just slip them over your regular shoes. And you can see inside here that there's actually two zipper layers, because, well, you can't just rely on one zipper layer. So there's one and then two that fully protect all your clothes. And the hood is, ta-da! Wow, that looks bad. And you can see that the boots have like a stud thing here, plus the zipper, which, there we go. I got bare feet inside these, but yeah, you can just slip your shoes inside there, no problems at all, and then goes the complete length. So thank you very much, Vincent. He's from San Jose in California, the heart of Silicon Valley. So let's rip this sucker open and see what we've got in here. It is quite a decent box. There's a whole lot of stuff, so this video could go for a while. And by the way, Vincent said he will be posting more comments on the stuff in here on the forum thread, which will be linked down below. And so if you have any questions about this stuff, Vincent is the guy to ask, and I'm sure he'll answer all questions. So let's have a look. We have some Photoshop chick. Alright, let's get down into the serious stuff. Here we go. We've got a whole bunch of envelopes to go through, and a whole bunch of cool stuff, all individually wrapped. Awesome. And there is some non sequitur stuff in here, not associated with that clean room stuff. And this is Sagan's picosecond pulsar, serial number 1. If you don't know, Vincent designed and built one of these Jim Williams pulse generators, and I think he was selling little kits of these some while back. So we'll check that out. And there you go, it actually comes as a kit, one of these nice little soft-sided Hammond cases, and a whole bunch of parts. This one is specifically for Sagan to put together. I don't think he's into SMD stuff yet, but anyway, I'll have to do a second video on that, build this sucker up, and just test it out. But yeah, I think it's in the order of 250, 300 picosecond rise time or something like that. And in this packet we have a bond out chip. He thinks it's for the 87C5532 processor. So I've done a video on emulator things in the past, and these were, really old school stuff used for emulators. So let's check this out. And here it is. It's an emulator board which plugs into your system under test like this, and you'll notice that there's 2 rows of BGA type pins like that, but the actual processor up here is a bond out version of the chip, which means it has access, a special version of the chip they manufacture, or they used to manufacture back in the old days before JTAG on-chip serial debugging all took over. It's almost completely eliminated the entire market and need for these special bond-out chips. Anyway, the manufacturers would manufacture a special version of each processor like this, very, very expensive, but you would get one of these just to allow access to all the internal stuff so that you can debug it. So all these extra pins on the chip allow you access to all the internal stuff, and that's why this bond-out version of the chip is actually bigger and contains more pins than the chip, in this case an 8051 processor that it's actually emulating. And in here we have some TQFP lead frames. These are the lead frames that are used as part of the chip manufacturing process. The die goes inside this and then the leads are formed and then it's encapsulated. Let's take a look. And here it is. It's actually quite long, and I will get the macro lens out and show you a close-up of this, but this is basically the copper sheet which the die, when they manufacture it, after they cut it out, they place it in the center here and then they bond over all the individual pads on the die over to each individual leg on there, and then this is what gets formed into the chip. So a chip like this TQFP package 1 is essentially made up of 4 different things. One is this lead frame, which is the copper lead frame with the individual pins, and then we've got the die which sits in the middle there. I presume they glue it onto the center somehow, and then the bond wires which they will individually then bond over to from the pad on the die over to the individual leads. So there's, a welding machine that comes down, and micro welding machine comes down and goes boop boop and wires each one of those individual wires over to each one of the pads. And you can see why it's called a lead frame, because it sits in a frame like this, and I'll get another angle. This is actually sunken down this part, and I'll show you the other side as well. At the moment all the pins are shorted out like this, but as you can see, once they're all bonded over and everything else, they would then slice off all of these pins somehow. I don't know whether they do laser or a big stamp or a saw or whatever. I'm sure Vincent can help us on that. And then these leads are then formed into the individual pins. And at a real shallow angle, hopefully you can see how that is actually sunken into the bottom of that there. And on the bottom side you can see how that's actually raised up like that. So on the top side it's sunken in where the die goes. And there we go, there's a bit better shot of that when the die just sits in the well like that, and then the bond wires go up and over to the individual pins. And after the die is placed in there and it's bonded over, then it's encapsulated, i.e. gunked, with the with the typical black plastic encapsulant that you find these chips in. And then once it's all encapsulated like that, then it's actually cut out. Then the leads are cut out and bent into your final chip. But of course your individual leads aren't actually copper, so there actually will be solder coated or lead free, solder coated, whatever type of finish that you order your chip in. And you can see how the ends of these little copper tabs aren't actually connected through to there, and that's actually quite a delicate little construction there. So they'd have to have, when they're bonding these, they'd have to have some physical support under there, so they'd have a custom well that this thing would sit in to actually support all these individual pins. Otherwise, when the welding robot came down and tried to apply pressure and weld the individual wire, the bond wire, from each pin over to the pad on the die there, then, well, it's going to jump around like a jumping castle there. So that's no good at all. So that would be fully supported. And we have some BGA test burn-in sockets. Some of them in here are for the bench testing for individual chips. Others are ones that go inside the thermal chamber for long-term chip aging. And these things are serious kick-ass. Look at that. Oh, if you have to ask the price, you can't afford it. Well, actually, you might be able to. This one here is, which is the burn-in socket, is about $1,000 worth, or over $1,000, and this board level burn test one is about $300 in quantity. So this is a PCB level zero insertion force ZIF socket, essentially for PCB level testing. And the way you undo it is you just unscrew that. It's got a lever on the side here, and then bingo, you can lift that up. And that material there is called Taulon material, and you know, it's a special type, special dielectric constant for high frequency stuff. And basically this is a for a specific number of type of BGA pin with that specific footprint. And what you would do with this typically is, here's the bottom of it, and you can probably see those pins sticking out the bottom there. Well, you would obviously design your board so that you can screw this into your board, and these tiny little pins there make contact with the BGA pads on your board. So instead of soldering your chip directly onto the board, you insert this zero insertion force test socket, and then you can plonk your BGA chip on there, and bingo. Yeah, you are going to get some signal integrity issues doing that, so you would have to take that into account. So obviously that would be very carefully designed with you know, the dimensional tolerance and everything else, just to give the exact right amount of pressure on the chip there, so you don't damage the balls when you screw that up. And after you screwed it up, you got a nice hole in the top, you can still read your part number. And yes, they are pogo pins. Look at that. We can push those up and down. So when you screw this into the board, of course, it applies just the right amount of pressure. They've got a little individual spring behind those. If you haven't seen pogo pins before, they're designed to give a fairly consistent amount of pressure onto the pad on the BGA pad onto your PCB, and these things work really well. So that's why they aren't cheap. I mean, you know, $300 a socket in volume, really, for a specific type. Yeah, they just take a lot of manufacturing. And you can see when I push my finger up from the bottom, push those pogo pins up, you can see that there looks like a crown arrangement to sit onto the, or to apply pressure to the bottom of the ball on the BGA chip. They would be specifically designed to get a nice even pressure on the ball and not damage it. And this sexy one with the brass screw top on here works exactly the same way. It's a different material though. This grey material is like a Teflon type material, good for up to 10 gigahertz. So that's why this thing is bloody expensive, you know, over $1,000 socket, no problems whatsoever. This one's got a bit of just a perspex on the back there, but it could of course go into the board, and these are designed to go into thermal chambers for long-term temperature aging and stuff like that for the various chips. Once again, it's a specific designed specifically for one particular type and pin count BGA package. And it works the same way. Just unscrew that, which provides the even pressure, and then you can release the lever like that, and ta-da, we're in like Flynn. And once again, we have the individual pogo pins down in there, and these are already been pushed up by virtue of the perspex screwed into the bottom of this thing. And once again, you can see the crown configuration on that pogo pin. It's got 4 little points there which wrap around the ball. And that's manufactured by a company called Winway. And here's an image from the Winway website showing that they also do really ultra high performance coaxial sockets as well that can go up to 30 gig, when just those individual regular pogo pins aren't enough, being they can actually manufacture specific devices tailored to your requirements. Whoa, man, don't ask the price on those. So you can picture hundreds or even thousands of these sitting inside some big climate-controlled chamber for, you know, days, weeks, months, being, you know, life-tested. So really phenomenal stuff, and that's why some chips are, you know, really expensive, because they have to be individually thermally tested in something like this in a big climate chamber. Probe needle time for probing dies and things. Awesome. Now, of course, to test silicon wafers, you've got to have a big automated test machine which comes down with, you know, hundreds of little probes which come down and then actually onto the pads on the bare die and individually test each one. And of course, performance can be an issue. You can't just come down with a set of regular pogo pins as we saw in those test sockets and then have a cable going off for, you know, even 30 centimeters to some sort of amplifier or stuff like that. So what we've got here is some Fet probes, which actually have a Fet Fet buffer right at the probe tip itself. And these, yes, if you can read that, 100 nanometer tip, nanometers, folks. And we have some regular probes for the less high frequency stuff, 22 microns wide, like that, with the actual point tip less than 1 micron. Absolutely incredible. And these are cat whisker probes, and you can actually make point contact diodes with this thing onto a wafer. So you can make a, you know, an old-fashioned point contact germanium radio with this thing. Anyway, this comes from the Micro Manipulator Co. in Carson City. That's still factory sealed for our protection. Let's open it up and get the macro lens on there. But basically, I don't think I'm going to have magnification good enough to see these tips properly. And that is the best zoom I can get on that. That's using my ×10 macro lens there. Look at that. So these are just the regular tungsten probes that would be used just for general purpose point contact die testing. And here are our tungsten probes, and you might think, well, yeah, okay, they're pretty huge, but what you might have to view this in HD, but in there you can see a tiny little 22 micron wires coming out of that. Absolutely crazy. That's with the 1 micron tip on it. Unbelievable. How do they even manufacture those? And there it is. You really do not want to go touching those with your finger. If you get that embedded in your finger, never get that bastard out. So I repeat, the tip of that is 1 micron, 1 millionth of a meter point on that. Whew. Now if you thought that a millionth of a meter was a small probe tip, this one is an order of magnitude smaller again, 100 nanometers, 0.1 micron tip on that. You might have to view it in HD, but it is right down there like that. This is actually an active Fet probe. That's actually a Fet, believe it or not, designed for basically high frequency performance, because you've got a tiny little probe tip there which goes down onto the wafer, and then this Fet, which then buffers the signal to go up the coax. Now if you're curious about the physical construction of the Fet, then that probe wire going down there, of course, that is connected to the gate of the MOSFET, and then the drain is connected to the casing of the pogo pin. Effectively, it's a coax, pretty much a solid form coax there, and the source is connected to the center pin of the coax over there. And they are pico probes from a company called GGB Industries Inc. in Naples in Florida. So they specialize and probably sell these things for an absolute fortune, and the only people who are going to use these are wafer test fabs. So these things are just so stupidly tiny. They actually need micro positioners to actually position the tiny little wire you can see maybe in HD out there onto the bare die. And that one's actually 0.1 picofarad gate capacitance with shunted with 1 meg. And we have some bare chips. In fact, chip on flex time. Let's go. Alright, this is the top side, so hopefully it won't fall out. So we're looking for some bare die here. And nothing yet. Ta-da! There we go. Got some lovely bare die in this carrier. Oh, still need the macro lens. And I really need a proper microscope to see that, of course, but you can see that it's a bare die, and you can see the bonding pads on there. It's absolutely tiny. I mean, the total diameter of that is, check it out, 1, 2, or just on 2.5 millimeters or so across. Absolutely tiny. This is the full ×10 zoom of my camera, plus the ×10 macro lens as well. And if you're curious to see the back of that die, well, there's not much to see there at all. Next up, we have ourselves a photo mask from Dupont Photo Masks. So let's have a look. We've got ourselves the carrier here. Look at the reflection on that. Beautiful. And it looks like they're a really very rectangular... Hello. There I am. Beautiful. Mirror finish. Fantastic. I'm going to have to probably get a light behind that or a sheet of paper to be able to see the photo mask. And when you need a poor man's light box, well, just get out your mobile phone and use one of those apps to turn your screen completely white. And now, ta-da, we should be able to zoom in and see. We're still getting reflections off the ceiling, which is really annoying, but we should be able to see at least as good as we can without a microscope. We can see the photo mask in there for the die. And there we go. We can see some of the circuitry on there. Really need a better microscope to see that, but you can see the edge there. They would be the, are they the bonding pads? Vincent didn't say what this one was, but obviously some sort of memory array architecture there. Something, because it's pretty uniform all the way along. And I don't know, could be some sort of PLD or something like that. We've got some I/O, presumably. We've got some I/O pads down the bottom of that, but yeah, not exactly sure what this thing is at all. And it's a very long, thin, narrow die as well, so beats me. I don't know. Vincent will have to clarify on that one. And the really interesting stuff has only just begun. Look at this. This is what's called a probe card, and we'll get into the technical details of it, but this is the probe head which goes into the wafer. We'll get down there and see the individual probes, but basically this thing comes down like this. This connects to the automated test machine for the wafer, and this thing basically they position each wafer and then each die underneath here, and then this comes down, the probes in here make contact with it, and then with that particular die on the wafer, and then tests it, and if it passes or fails, then there's an ink squirter in the middle which can then squirt the die as passed or failed. So this is all part of a much larger big head, but this is the test probe card for it. And yes, these are individually made by hand for each and every different chip variation. And if you think the top's impressive there, of course there's really hardly anything soldered on there. It's just had a couple of, well, there's one relay on there, a couple of tantalum SM and a couple of other MISC SMD caps, but obviously these are all points that are designed to be connected to. But you really want to see something impressive, let's flip this sucker over. In fact, let's see the first impressive thing. Have you ever seen a board that thick? That is 8mm. I'm not kidding, that is an 8mm thick PCB, 24 layers. Unbelievable. Imagine what that costs alone. Is this the funkiest thing you've ever seen or what? Well, let's take a look at the center here, and yes, I will get the macro lens on that shortly, but basically all individually hand wired. These are all handmade. I don't know who sits there and hand wires this thing, but anyway, these wires aren't stripped. They've got individual sleeves on them which connect to the, I'm not even sure how many pins are in there. I don't think I want to go in there and count them, but we'll get in there. It probably looks like, well, on my screen of the camera, it looks like one big contact at the moment, but there's probably, 100 contacts on each side or something like that. So, woo, this is incredible. And this PCB ain't made in China, that's for sure. There's obviously multiple wires bonded to the same point there. Bonded, fancy talk, soldered onto the same point. And look at that, all just individually flowing into just one side of that chip. And then if we bring the point contacts into view, I don't know, can you count those? I'm not going to bloody well count them, that's for sure. And that's just crazy. Look at all those point contacts there. It looks like there's a couple of layers there, actually. That is just insane. If I get my probe up in there, those things are pretty bloody solid, actually. They're really hard to budge. Oh yeah, I think this one has seen better days, that's for sure. I mean, look at all those, they're just bent. Nah, these are all ruined, but it does look like there are multiple layers And they're the ones who make this advanced probe ink. This is probably all they do. And that's why it looks like it's dual row, because if you get right down in here, sorry, my probe's just way too big for this. There is actually dual height, so they come in one on top of the other, but then they actually spread out to give you a higher density here. So it is just the one row of pins along here contacting to the one row of bonding points on the die, but then of course that pitch there between those contacts is too small to then drill individual holes through this head and feed them through. That's why they have to split them out to one above the other to get the pin pitch. I'm not sure what the diameter of those things are, but they've got to feed each one of those through with their individual wires coming out. That's just insane. And yes, these are actually handmade, each individual one. Somebody actually sits there and feeds each individual wire through and then forms them and, and makes sure they're the correct length and then probably, I don't know, glues them in place or something. Just, God, how long would it take you to assemble something like that? I mean, God, unbelievable. I'll never complain about a rat's nest again. And hopefully you can see there that this entire thing, that entire center pin structure is actually raised up so that this thing can actually come down and make contact with the bare die on the wafer. So you might think, well, this is insane. I mean, to go to this level of complexity and have all that automated testing right on the bare die there. I mean, wouldn't it be easier to just assemble all the chips onto those lead frames we saw earlier, injection mold them, and then, well, maybe even probe them at that stage or something like that? Well, each stage of the semiconductor manufacturing or chip manufacturing process adds extra cost. And even though these things are ridiculously complex and, ridiculously expensive to build these automated test systems, once you've got them and you've paid that NRE, that non-recurring engineering cost to set up the chip, it is actually cheaper to go around and then move the die underneath and probe each one and then put a little, black or red dot on each chip that actually fails. So then when you go to package them up, you only have to package up the good ones. So you're only paying those extra manufacturing steps if the bare die is known good. Because of course there's a thing called wafer yield, and on average you're only going to get a certain percentage depending on the technology. If it's really bleeding edge stuff, and your clean room's not absolutely perfect, you're going to get X percentage or even quite a high percentage of failure rates on your die. So it makes sense to go to all this effort to test each one. And this is just the head. This is just the probe head, let alone all the rest of the automated test machinery and all the mechanics and the hydraulics behind the whole thing and all the automated handling and the software and the ATE machines themselves. And forget it. But hey, it's worth it. This is why these, wafer manufacturing and testing fabs, because the same wafer, by the way, may not be tested in the same fab that it's actually manufactured in. So they may actually ship them somewhere else to actually be tested and then packaged up. And I'm not sure if you can notice that here, but that looks like a gold sleeve over that. They don't actually strip this wire. This is not like enamel coated wire you might be familiar with. The wire is just bare, and then they weld or solder that on first, and then they slide this sleeve over the end of it. Each one of those is done by hand. And these are supposed to have a contact lifespan of not in the tens of thousands, hundreds of thousands, or even millions, but billions of contacts. They basically do not wear out. And now we have some wafers. Yes, these are full 300mm wafers from a fab, and apparently these carrier boxes rare as hen's teeth. So Thanks to Vincent for actually getting those. Otherwise, you cannot transport these things. They will just shatter. And I have to be incredibly careful with these, handle them by the edges. Otherwise, and if you drop it, you'll shatter it. And these things, silicon, oh man, sharp as razor blades. So you're really just slice you to bits. So really, we have to be very careful here. But there's several wafers in here, I believe. See what we've got in here. We've got some filler. And our first wafer will be, no, not under there yet. Almost there, almost there. Ta-da! Oh, look at that. Now this wafer here is actually a silicon germanium type wafer. And no, this isn't the full 300mm one. There are larger ones underneath. And so this is a smaller wafer, and this is actually has been sawn. So all the individual chips, when we get up close to it, all the individual die on there. So this is called a wafer, and then you've got the individual die on there. So each one of those is an individual chip, and this has actually been sawn. So we can lift, well, then the machine can lift off the individual die and then place them on those frames which we saw at the start of the video. And that's of course after they've been tested, when our big probing plate moves over this, or this could be fixed, and they move the wafer underneath, and then it goes down, boop, and then steps along and steps and repeats each single one of those die. I don't know, you want to count them, but yeah, this thing goes around and then tests. You know, it could take hours, depends on the complexity of the test, to test a wafer, or a day or something like that to test an individual wafer. Now as you can see, the wafer is round, and they're not shy about just going right to the edges there and trying to maximize the absolute maximum number of die that they can fit on a round wafer like this. And these are sawn with a diamond saw. A diamond saw just comes down, you know, real precision stuff, goes along there and actually makes all those cut marks in there. And I'm not sure, we should be able to lift off those, but I probably don't want to. There are some that have already been lifted out of here. You can see that there. They've either fallen out or have been lifted out, and they're individual chips. So this is how many they can fit on, what's this, a 200 and just over 200mm wafer, I think. So there's a close-up of that, and you can really see the saw marks. How this is real precision engineering, folks. Absolutely phenomenal. Jeez, look at that. You know, a saw actually comes down and cuts these things. It's not a laser, mechanical saw. And that is a sticky rubber membrane like that. And should just be able to lift those off. Can pop them out like that. Look at that. Brilliant. Just lift that out, and we should come to another wafer. Ta-da! Looks like we've got another 200mm one. And this one, I am told, is an 8051 processor. We're not exactly sure what variant it is, but that is, you know, that's a reasonable sized die, actually. That's like 10mm square. So there's the edge of the wafer. I'm not sure what happened to these ones over here. Some sort of chemical process went horribly wrong there. Not sure, but it doesn't matter. It's all about the total yield. And there we go. We can see the chip itself, the bond pads around the outside. This zoom ain't the best, but yeah, that is some variant of an 8051 processor. And fortunately, this one is already nicely encased for us. Look at that. And you can see the bottom part of that. Once again, this has already been sawn as well, but love the colour in that. Doesn't that look stunning? Hello. Ta-da! I can see myself in a wafer. And last, but certainly not least, we have a 300mm wafer, which is basically as big as these suckers get. And look at that. Oh, that is enormous. And I definitely do not want to be touching this sucker or trying to lift that out, or if I do, got to do it via the edges. Incredibly brittle, as I said. They will shatter. So anyway, Vincent has given me a frame to try and put this into, fingers crossed. But I won't do that in this video. I will, if I can successfully assemble it in a frame, I will, and then I can have the thing up as a showpiece. Now this one hasn't been sawn at all, so this is just the original die, straight off the line before it's been handled. And yeah, not that. It looks like all that stuff on the outside is probably where they've spun coated stuff, would be my guess. Or, you know, Vincent would be able to tell us that, or anyone who has any experience in the actual bare silicon wafer manufacturing thing. But I think that's, you know, how they put the layers on these things. They actually spin them out and apply coatings, and that's what it looks like. It looks like something's just dripped off the edges there. Anyway, there's our chip in the middle. It looks like 2 rows there of bond pads. So this one looks like very serious business. I'm not sure what chip this is at all though, but yeah, it's a biggie. And I've just got one of these cheap USB microscopes here from 40 times to 800 times. They're not the best things, but they're really cheap. And I will endeavour to have a look at a few things under here. Please excuse the lack of video capture here. I'm just pointing my camera at the screen, but it should be good enough. And there we can see the lead frame under there. We can see how the copper, it doesn't look, you know, it doesn't have that gold sort of coppery color under here because probably the LED bright light is too bright on that. But you can see how the leads are formed, and then the individual bond pads there, which then get jumped over with the bond wires onto the die. And here's one of these cat's whisker probes, and that's at minimum 40 times zoom, and you can see the sharp point on that and the weld of the, is it tungsten point, I think, on that. Anyway, that is quite interesting. That's not a bad shot at all. Look at that. And that is the probe tip superimposed on a 0.1 millimeter grid. And now we're looking at our tungsten probe tip, and I'll attempt to move this along here. It's incredibly difficult. This is the one with the 22 micron shaft there, and the less than 1 micron probe tip. I mean, you can barely see it in there. It's just ridiculous. I mean, this camera is, I'm not sure what the current zoom setting is, but I'm not even close to, you would really need a real proper microscope. These microscopes, you know, claim to be times 800 times. They're just garbage. And this here is one of the Fet Probes, one of the active probes that we saw, and you can see the contact wire going off. Once again, this is not the smallest one. This is not the 100 nanometer tip one. This is the 1 micron tip one. And if we have a look at the other side of that Fet, woohoo! Look, can you actually, is that clear in there? You can actually see through that. That's actually quite remarkable. Really? Look at that. Wow. Unbelievable. You can see the light through pinholes on the other side. And yeah, you can see those pinholes through that clear, I presume it's some sort of clear epoxy or something like that. Not really sure. The physical construction of that Fet. It's just remarkable. But look at the contact probe just coming off there. It's crazy. And we have ourselves one of those bare dies that we had in that little die box before that had like 100 of them in there. And well, I'll see if I can get the best zoom on this USB camera, but oh man, it's just so tricky. I can, but it's just horrible and pixelated. Yeah, these USB cameras are just a joke. They're, you know, when you try and get in for really serious magnification, just don't bother, really. But anyway, we can see part of a, well, we can see like a quarter of the die there, and we can see the bond pads there and there. We've got some sort of marking there. We might be able to make that out if we could get it a bit clearer, but that's pretty horrid. So just to show you what this USB microscope can do, I've got it flat against the paper at the moment that die is lying on, and that's right down at the bottom end. So that's like in the times 40 position. So it has one focal point there, and without adjusting the height of it, you zoom in, zoom in, zoom in, it's absolutely useless for anything else until we get to a second point where we can actually get another focus at a higher zoom. I mean, that's right at 800, so, you know, assuming it's linear, it might be like 600 times or 500 times or something like that. And that is absolute maximum times 800 zoom which we can get on this thing. But look, it's just horribly pixelated. So an awesome dual thumbs up to Vincent Himpe, free electron on the EEVblog forum, for sending in all this fantastic, very difficult to get semiconductor manufacturing stuff. So I hope that's given you some insight into, you know, some of the stuff that goes on inside semiconductor wafer fabs and testing. And if you want to ask any questions, I'm sure Vincent will be happy to answer them on the forum. So the forum thread will be down below and he can answer all your questions, I'm sure. So if you enjoyed that, please give the video a big thumbs up and give Vincent a huge shout out. I'll link to his website, Silicon Valley Garage. That'll be down below as well. Check it out. He's written a few books as well, which we've had on the mailbag in the past. Awesome. Thanks, Vincent. Best mailbag ever. Catch you next time. I look like a total dick. Thanks, Vincent. Hammer time!